Now for the next session, we have software-defined memory is here. It performs like local memory, scales, and works on any hardware. And for that, we have John Overton, CEO of Cove, Narendra Narang, Chief Technologist, Telecommunications, Red Hat, and Chalapati Neti, Head of AI, COE, Swift, with us. Please welcome them.
Hi, I'm John Overton. I'm the CEO of Cove. We are possibly the biggest little secret that you don't know about yet. Hopefully that's going to change here soon. We've been letting customers do some really interesting things for a long time. Over a decade ago, we introduced a sub 10 microsecond block device. We now have memory working properly, fully software. So when someone says there's a memory wall, I think we could say a couple of things that we could agree upon. Computing is now data-centric. I don't think that's controversial. If it's data-centric, it has to be memory-centric. I don't think that's controversial either. If it's memory-centric, then you go large or you go small, and all of a sudden you have new challenges. To expand gene sequencing and AI, memory requirements expand quadratically. Let it hit you, right? Now imagine LLMs, same thing happens on the edge. These are truths of what's happening. Now, what do we do? What does our software do? We are pooled memory. We work on any kind of server, any kind of processor, any kind of anything. It works right now. You know, upgrade hardware, you don't have to do anything. It not only works across the rack, we route memory across the data center. We have placements in unnamed locations for over 10 years. This isn't kind of real. You don't any longer think about how many DIMM slots you have in a server. You don't think about how much memory. You want a petabyte of memory, no problem. The limits are any AMD 64 spec compliant processor, and the performance is limited to hardware theoretical plus or minus a few percent. Scale that any direction that you want. What about stranding? So let's say that we start throwing lots and lots of memory at things. Well, memory is really expensive. Now you strand it. So do you spend more time on power, more time on stranding, more time on cost on memory to solve the problem? Or how about just route it? Now, this eliminates memory constraints. It eliminates all kinds of things. So the so-called question that we all have been plagued for a while, what's the latency? What if I said to you, we can solve in software the latency issue? Again, let that sink in. It can be done. And I would say the next is that it's available today. You can get it. It takes 40 or 45 minutes to install. It works on anything. Now, the final thing I'm going to say is don't believe anything that I just said. Validate it. Okay? Don't trust some guy sitting up in a sweater. Talk to these guys. These guys know a thing or two. I like to let our software speak for itself. And along those lines, I'd like to hand it over and get to it.
So, as dry as this topic is, I'm going to try to make this a little bit exciting. I'm going to do this by telling a story, right? And as you heard, you know, or John introduced me, and I've worked with, my job is to work with customers. And I've traveled the globe working with a lot, you know, some of the largest operators all over the world. But everything you'll see here has been centered around our customers and the feedback we get from customers. So our discussion centers mainly around memory-hungry applications, right, that are at the forefront of technological advancement. And these applications really have an insatiable appetite for memory, relying on it to process and analyze vast amounts of data at breakneck speeds. Now, the quest to meet the surging demand for this memory, that needs to be increasingly efficient, involves not only advancements in hardware, but also software optimizations, and to ensure that we can do more with the memory that we have already available and make this memory accessible to the discrete compute components that we have in the data center. So let's talk a little bit about just or explore memory a little bit. And it's categorized, for the laypersons in the room, it's categorized as basically volatile or non-volatile. Volatile, essentially keeping when it's not powered, it's not going to persist the data. And then non-volatile, which will persist it even when it's powered off. And then it's characterized by several attributes. Its density, which determines really the volume of data that it can store. The voltage, which impacts its power consumption and efficiency. And this is the topic that I'm going to continue to talk about. And its fidelity, or really the reliability, or for storing and retrieving the data accurately. So the development of more energy efficient memory modules, the adoption of advanced power management protocols, and the exploration of new architectures, everything you've seen since this morning, represent pivotal steps, but not without limitations. And what are those limitations? To achieve increasingly higher densities and storage capacities, there are, many cells that are packed together in these small areas. But as you get smaller and smaller, it makes them more vulnerable to electrical leakage, and they need even more power to persist that data. And memory controllers, although they're improving, are also constantly consuming more power as they refresh their contents. Engineers and designers, and for those of us in this room, are confronted with the trade-off between the density and the fidelity, and as they seek to maintain this delicate balance, but while continuing to push the limits of the technology. So our discussion also brings us to the intricacies of supply chains and their impact on the cost of memory. The global nature of the supply chain, as we've discovered, through the pandemic, makes manufacturers and consumers alike susceptible to a wide array of disruptions that lead to a volatility in both availability and pricing. Now, as indicated by the trajectory, you can see that the exponential growth in data is what's really driving, and the consumption of this data is really what's driving this unprecedented surge in memory demand. And this is what underscores the compelling need for the continuous innovation, while also navigating the challenges of the supply chain volatility. Now, we're on the cusp of a paradigm shift, moving away from traditional dedicated memory models towards more fluid and efficient shared models, and redefining the very fabric of memory architectures to meet the demands of this modern computing. The traditional dedicated memory model, where each processor or system has its own allocated memory, is becoming a bottleneck in terms of scalability and efficiency. By transitioning to a shared memory model, you can imagine pools of memory that are not bound to specific processors, but are dynamically allocated based on need, to enhance the efficiency and to significantly improve the flexibility of this memory allocation. The edge represents a distributed computing paradigm, and the relevance of this new memory model becomes even more pronounced as the processing moves closer to the edge. And horizontally scaling memory across the edge enhances the resilience to achieve unprecedented levels of efficiency and scalability. So how do we manage this complex pool of shared memory? Enter software-defined memory. Quite simply, software-defined memory abstracts the memory layer, allowing for the dynamic allocation and management of memory resources through software. This simplification is a game changer, enabling more agile and adaptive memory architecture that can respond in real time to varying compute workloads and their respective demands. At its core, software-defined memory addresses a critical challenge. It brings a dynamic adaptability to memory allocation and provides an elegant solution by enabling the compute servers to access a shared memory pool and utilize memory resources beyond their physical confines to dramatically improve memory utilization. There's many benefits to this approach as well. In the first case, it saves time because business-critical applications can now rapidly adapt to the changing requirements with automated memory allocation and its management. and reduced manual intervention. The efficient use of memory resources within the system or across the system also reduces waste and lowers energy consumption, translating directly into lower operational costs. And this is something we'll show in a few slides in a moment. An intuitive software layer reduces the complexity and makes memory management more accessible and less error-prone. Now, this is all accomplished without intricate configurations and constant tuning to enable workloads to run, without compromising on the size of the data set in memory, which is extremely important. And I want to stress this, without any code modification. Security is also enhanced by the software-defined memory by ensuring that assigned memory instances are purged to a zero state before allocation, and this guarantees that no residual data from a previous task remains, and that each application has access to a clean, secure memory slate. Now, the basis of our work, and this is the exciting part, and that I was looking forward to, is it combines some of the work that we collaborated on with Intel with respect to the Kepler project that is part of CNCF. And this really leverages the concept of both C states and P states in the Intel processors today. And again, for the laypersons in the room, quite simply, C states are idle power-saving states where the processor reduces its power consumption when not executing tasks. And the deeper the C state, the less power the CPU consumes, but of course with the trade-off that it also takes longer to return to its operational state. And P states, or performance states, which allow the processor to run at a different voltage and or frequency level, reducing power consumption while trading off some CPU performance. These controls allow for the finer-grained and more responsive performance to swiftly adapt to the varying workload profiles and achieve the desired balance between performance and energy efficiency in the modern distributed computing architecture. And this goes back to some of my earlier slides where I talked about the need to drive efficiency by some of the designers and the engineers, because you're the ones that are building the memory, and it's up to us to use that responsibly. Now, these findings are not intended as mere comparisons with alternative memory solutions. They are instead a suggestion or a reimagination of memory architecture paradigms to really set new benchmarks for computational efficiency and performance. The rigorous analysis of the empirical data that we collected through the testing in the following illustrations, they collectively articulate a very compelling narrative on the efficacy of pooled memory, utilization via Cove software-defined memory across a spectrum of memory speeds ranging from 3.2 to 2.2 gigahertz. Now, we did this specifically to better understand the correlation between memory frequency and bandwidth. That is the amount of data transferred to and from the memory over a unit of time. Since adjusting the frequency doesn't always translate directly to higher bandwidth or overall system performance. There is a dependency on workload characteristics, on memory architecture, the controllers, and even how well the CPU is equipped to consume this effective bandwidth. Now, the first four charts here really show a consistency that regardless of memory speed of this pooled memory, ranging from 3.2 all the way down to 2.2 gigahertz, pooled memory has negligible performance impact for CPU or to the CPU performance. And in fact, in some cases can be even faster than local memory for memory performance. So again, these are visual representations that really serve to provide a deeper understanding of the interplay between memory, speed, and CPU in the context of pooled memory that use Cove software-defined memory. They really demonstrate that the integration within pooled memory configurations, irrespective of the memory frequency, has minimal impact on the CPU performance metrics. Now, this revelation was pivotal because conventional wisdom posits a trade-off between memory pooling and CPU efficiency. Even more intriguing is the evidence suggesting that in certain scenarios, the application of pool memory orchestrated by Cove can outperform traditional local memory setup, particularly in metrics related to memory performance. And these results, are really based on the strategic implementation of the Cove algorithm, which may be attributed to the optimization of CPU cache hierarchies and how the algorithms navigate and manipulate the intricate layers of memory, access protocols, optimizing data retrieval and storage processes to harness the performance improvements. On the last of these charts, you really get to see on the graph number 5 and graph number 6, the relative amount of CPU overhead for using the algorithm, and this is represented both as a comparison or a direct comparison when we do use Cove and when we don't use Cove. And finally, graph 6 shows that as a result of using the algorithm, there is a massive improvement in the efficiency of memory access due to the optimizations of CPU cache hierarchies. From addressing the needs of memory-intensive applications and infrastructure to grappling with the limitations of memory and the hidden costs of memory, the path forward is both complex and exciting. The dynamics of supply chains and the relentless demand for memory highlight the vital importance of innovation, resilience, and sustainability in shaping the future of computing. The shift towards a shared memory model facilitated by software-defined memory represents a significant leap forward in our quest for more efficient, scalable, and resilient computing architectures. Now, this evolution is particularly pertinent in the context of the edge computing scenario, where the traditional paradigms of memory allocation and management fall short. In conclusion, the case for software-defined memory is more than compelling. Embracing software-defined memory is as a cornerstone technology in the evolution of computing infrastructure will transcend traditional physical limitations and adapt applications dynamically to pave the way for the next generation of computing infrastructure. Thank you.
And before we move to Chalapathy, I'd like to, I've known Narendra for a few years. When he says this was rigorous, all the results were tested 7 times and averaged to eliminate experimental skew. And I think in terms of the CPU cycles, there were tens or hundreds of billions of tests or of CPU cycles used to express this. This was very rigorous. Similarly, Supermicro is involved in this. We want to thank them for making the hardware. And to be utterly clear, there are no code changes here. What you just saw just plugs in. And it's in some cases faster. Now, this was designed to push the limits of what we could come up with using StressNG. We use StressNG because it's a common application. Now I'm going to switch this over to my colleague Chalapathy. He's building some of the coolest stuff, I think, on Earth. I'm just going to hand it to you, and then you go from there.
First, thank you, and it is a true pleasure to be addressing all of you. I'm the head of AI for Swift, and I'm going to talk to you about a problem that we are working on that really starts requiring these kinds of shared memory. So Swift, as some of you may know, is the financial backbone of the payments world. Roughly the equivalent of the global GDP flows over the Swift network in 3 days. We have operate in 200 currencies, that is 200 countries, 200 currencies, 2,700 plus corridors, and about 15,000 payment rules. About 11,500 institutions across the world using this network. We chose to, given our footprint, focus on a very important problem for the financial industry and financial crimes, that is payments fraud. Payments fraud is roughly $485 billion, written by the CEO of NASDAQ and LexisNexis. And out of that, roughly 200 billion is the operational spend in identifying anomalies, assigning true or false positives for fraud, or whether it's a duplicate or a mistake of some kind. Roughly about close to several 100,000 to 1 million suspicious activity reports are submitted, and only countable on your fingers are actually investigated. So there's a huge ability for us to improve the state of the art and move the needle on addressing and be a few steps ahead of a fraudster. So based on our footprint at Swift, called the Payment Control Service, which screens every payment for anomalies that underpin fraud, we chose to embark on this ambitious journey. 1.0 is trying to use the entirety of the Swift network, again, the data I described, to detect anomalies that underpin fraud. And we're actually well on the way. We are demonstrating roughly about 40% to 100% improvement by using AI compared to the current rule-based system. The second step is to be able to do this at line speed, meaning literally we do about 20 to 40 transactions per second. We'd like to go to 300 to 1,000, which is where we start requiring efficient AI infrastructures for inference that give us this kinds of speed. And the next anomaly 3.0 is the Holy Grail. So in addition to using this richness of the Swift data, we are planning to use privacy-safe, federated AI technologies that allow us to pool the data with our customers to create what we're calling foundation models for anomaly detection that underpin fraud that'll be industry-leading. To enable this progression, we've actually, in partnership with C3.ai, which is our AI ops layer, put on Red Hat OpenShift container platform to enable hybrid cloud, multi-cloud ready platforms for the future. And we've been partnering with our friend here, John Overton and Cove, to create a pool of software-defined memory, because our goal to improve the speed of computation is to enable both parallelism and having a pool of software-defined memory that you can share across these multiple processors in a way that allows these transformer-based foundation models to really be effective, both for training and inference. Our initial experiments, again, initial, have demonstrated that by using this stack with Cove enables us to get roughly about 60x improvement compared to a vanilla virtual machine running these types of workloads. And watch this space for future results in this arena. Thank you.
We'll take some questions, but I'd like to highlight a couple of things of my colleague, Mr. Netty. Swift transfers 93% of all money on Earth. The stakes can't be higher. They're in the process of creating modeling that will solve financial crime, potentially. Just to give a little perspective, before Swift, people put gold on boats and floated them around the world. That's how they made payments. Then Swift came because of his work and some work that we do also with some outstandingly good people in Belgium. There's the potential to do something that no one even thought possible. And in fact, that's what leads to questions. If you in the audience are interested in the art of the possible right now, we're it. Use OpenShift. We'd like to open up questions, any questions of any variety. If anybody has any.
Mention of, hi, Gene Bosman with Cloud Architects. I just want to know, we've heard a little bit today about optical interconnects, and people always say that it's really far away. Do you think that there's some near-term use that you can imagine or plan for in the near future? And if so, what is it?
Anybody want to,
The answer is yes, but there's things we can't talk about yet.
Yeah, but generically, how would it be used? In the context of the whole group, what would be?
Yeah.
It would serve as the interconnect, purely as the interconnect. The memory would still function would still have the same behavior that John described with the same algorithms functioning at each end. It's merely the interconnect that would separate the compute from, or I should say, the data from where it would need to be computed. Absolutely.
Oh, 100%. Sorry, I just want to tee off a little bit more on this. I mean, let it go to the back of one's brain. We're talking about having node code changes and having arbitrarily scaled memory on COTS, absolute commodity. Node code changes, period. And we're talking about these performance levels, 60 times. I don't want to be casting aspersions, but the results they got were 60 times apples to apples compared to a very big famous vendor who is in this room. I mean, but I don't think they want to talk about that. Like, this is real. It deploys right now.
And just to add to that, I mean, where we're seeing a demand for this, again, going back to customer demand, right? My work takes me to a lot of our customers, and this is in the context purely of where they want to create these GPU farms. And you need to have, and the data isn't always localized, right? And moving data is expensive as well. So we have to be able to account for these new architectures and the scale of what needs to be accomplished with what you described.
And one more, just because I think it's a really good question. If one were to consider optical, you could consider different distances. Right now, we route memory regularly across the data center. This is many hundreds of feet. We hide that latency. The numbers that you just saw up here, those are across 20, 30, 40 feet of cable, something like that. I don't remember what it was. It doesn't matter is the point. When optical starts coming, you can reimagine the way to use data on much vaster distances, and we'll still hide the latency. There's the question spot on.
So SDM, CXL, and what you're doing here, are you using InfiniBand then as your underlying layer to run your software-defined memory?
Where?
I'm over here. I'm hiding behind in the corner here.
Gotcha. So we do use InfiniBand. Our software is divined to be modular. So we don't care about the interconnect as long as it's serialized. InfiniBand is the most widely used one. We aren't doing anything with CXL. From our perspective, that's an interconnect. Rocky would be another one. PCI Express would be another one. If we had customers wanting to pay us for that, we'd be happy to do it. It's just an interconnect from our perspective. The whole approach that we have is really different than people might imagine. So we've worked on this problem well beyond a decade, this one problem of hiding latency. We've got a whole bunch of work on this. And the very first thing that we did is we made ourselves deliberately agnostic to any hardware component. I think we support all 57 of the commercial Linux kernels, for example. Everything we did is upstream compatible. I mean, and the list goes on. We really did spend time making it be built properly. So things like that question and its implied questions, what do you want? No problem. I hope that answered your question. Okay, thanks.
We've got time for one more question just here.
This question is for Chalapati. I'm so excited that you're solving such a huge, big problem. But I would love to know that why this problem is continually exponentially growing and what industry or the company is not doing right, which could be prevented to actually get this exponential curve down.
So it turns out the bad news is it is going to grow even further because of the real-time nature of these payments. And people come to instant payments like FedNow and other places. The ease with which you can commit fraud becomes higher. Second, with the advent of currencies like crypto and CBDCs, where you'll get a level of anonymity that was not possible before, these problems will be further accelerated. So the goal is not to say it won't grow, but the goal is to say, how do we use technologies to stay ahead and reduce the problem?
And I'll add something because I know that Chalapathy won't want to speak about certain things that we're working on and probably can't, and I can't either. But I can say that Swift is not shy about confronting this, and I'm seeing the work. It's ridiculously good. I think the potential that where Swift is in the next number of years, I won't say when, is equivalent to not having to put gold on boats except for fraud. So I'd like to say as we wrap up, really don't trust anything we've said. It's easy to validate every daggone question that we have here. That come see us at the booth. We can have a chat with it. It's if you want to do something right now and don't want to wait 5 or 10 years, come talk to us. Thank
And
you
I'll
very
just
much.
say that to that question, that is exactly one of the premises that prompted this work.
Yes.
Because we wanted to start thinking differently about how we can do what you just asked.
Great question.
Thank you, panelists,
Thank you.
and thank you, Cove.